Hey, thank you very much. I'm really grateful for the chance to give a talk in front of a large audience like this. Yeah, I really appreciate it. And yeah, please do interrupt, even if it's not an urgent question. I just start getting nervous if nobody interrupts me. So you'll help me out if nothing else, okay? Okay, so I'm going to be talking about Hamiltonian truncation. And don't worry, I'll explain what that is. Hopefully you have some idea what an effective field theory is, but I'll talk about that too. This is some work that has been a long time in gestation with Tim Cohen, Rachel Houts, and Kara Farnsworth. I saw that, I think Kara is in the audience. Yeah, let's get to it. Okay, so the first thing I'm going to do is tell you what Hamiltonian truncation is, because it's not something that I'm sure most of you think about. And it goes by, in case this is helpful, it's also called the Rayleigh-Ritz variational method. It goes, from the name, you can sort of see that it goes back to the very early days of quantum mechanics. The idea is very simple. The idea is you choose some basis of states, which I call here I. You guys can see my cursor, I believe, right? So you have some states I, right? And the Hilbert space is infinite dimensional, but you truncate it by just keeping n states, okay? So you, just like any variational method, you have to choose some states, and here the states that you choose are linear combination of this state I. So we can think of this as a truncated Hilbert space for the full theory. And then once you've chosen a truncated Hilbert space, the Hamiltonian is just a finite dimensional matrix, okay? And you just find the eigenvalues, approximate the true eigenvalues by the eigenvalues of the finite dimensional matrix, okay? So this is very commonly used in quantum mechanics. And one of the nice features of this is the so-called min-max theorem. You're all familiar with the idea that if you make a variational estimate for the ground state, then the variational estimate here in blue is going to be strictly larger than the, well, not strictly, but it'll be larger than the true ground state. But in fact, if you use this version of the variational method, then all the excited states of your approximate Hamiltonian are also larger than the true ones. So you actually are getting, it's sort of a variational method that you can hope to use for the excited states as well, okay? So now what I want to talk about is applying this very simple idea to quantum field theory, okay? So let me just comment very quickly on some of the differences, or some of the important differences between quantum mechanics and quantum field theory for this. First thing is that in quantum mechanics, there is no absolute zero of the ground state energy, only energy differences are physical, so we don't really have a min-max theorem for the energy differences, unfortunately. The other thing is that I now want to think of this as an effective field theory, okay, rather than just a variational method. So to sort of formalize that, I take the Hamiltonian of my quantum field theory and I write it as some free Hamiltonian plus interactions. And this truncated Hilbert space contains all the states up to some total energy ET, where I'm now measuring, for the purposes of this cutoff, I'm measuring the energy in terms of H naught. So I take my free Hamiltonian, that defines some energy, which is of course not the true energy, which is the true energy eigenstates or the eigenstates of the full Hamiltonian, but I use the unperturbed Hamiltonian to define my, my truncated space with some energy cutoff.
Okay. Markus, do you mind if I interrupt you?
Absolutely, yes, please.
Just a naive question. You keep on talking about Hamiltonians, but as you very well know in QFT, we normally talk about Lagrangians because of the issue of defining the Hamiltonian for light and things like that. Are there any subtleties when you consider these objects, or is trivial?
Well, for gauge theories, the Hamiltonian is very non-trivial. So that's there's some additional issues having to do with gauge fixing and so on. I'm going to be talking about very simple theories here, like, for example, phi-4 theory in low dimensions. And for that, there's absolutely no issue. You'll see the Hamiltonian very explicitly later. Okay, so yeah.
Okay, thank you. Thank you, Markus.
Okay, thanks for the question. So we think of the truncation parameter as a high energy cutoff, right? In fact, it's literally energy now. When we talk about a high energy cutoff, usually in a Wilsonian sense, it's actually not energy. It's something a little bit different. Okay, and so the Rayleigh-Ritz approximation, where I just take the matrix elements of the Hamiltonian in that basis, I think of that as only the first approximation, just like in effective field, sort of like tree level matching in effective field theory, okay? And this is most of what's been done has been, there's a history of this, this sort of raw truncation type cutoff, okay? It actually, I'm not going to give the full history because it's been rediscovered multiple times. It's a bit interesting, but I don't really have time for that. But it was first shown to be able to give interesting results in 2D quantum field theories by Yurov and Zamolodchikov in the early 90s, where it was called the truncated conformal space approach. It was used in flows of 2D CF, flows between 2D CFTs. And it's been more recently, the question was asked and it was investigated, the question, can we improve this method to get a precision calculational tool for quantum field theory, perhaps in higher dimensions as well, okay? And that goes back to 2014, and these works here, they led to a revival of this subject, and there's been a not terribly large, but sort of dedicated community of people that have been investigating this, okay? So there is,
Markus?
this is not, yes, please.
Sorry, I should have asked this earlier, but this, when there's like renormalization, is EI, does EI include the correction or?
I'm going to be talking about, I'm going to talk about renormalization near the end, okay? I'm going to be first talking about a theory where renormalization is essentially trivial, just sort of separating the issues, right? Like when we teach quantum field theory, we don't start with renormalization, right? And so I'm going to, but I will get to that more in the end, and there definitely are subtleties about renormalization. But you'll end up seeing that it's not so different. There's some crucial differences, but it's not maybe as different from ordinary EFT as you might think. Okay, but it's hard to answer these questions. I kind of need to build up to this. Okay, so hang on to that. Okay, thanks for the question. All right. All right. Okay, so let's try to embrace this idea of Hamiltonian truncation as an effective theory. Okay, so some comments about this. First of all, it's one of the ways that it's different from a conventional EFT is that when I'm done, my EFT is not a quantum field theory. Okay, it actually has a finite number of states. So it's quantum, not only is it quantum mechanics, but it's quantum mechanics with a finite dimensional Hilbert space. Okay, so that's something to keep in mind, okay, on this truncated Hilbert space that I've been defining. And I'm going to call this Hamiltonian truncation effective field theory. So to construct this thing, I'm going to follow the EFT playbook, which should make everybody here very happy, right? So what are we going to do? We are going to define the effective theory by matching some physical quantity to the fundamental theory, right? And we're going to be considering, in this talk, I'm going to be considering quantum field theories that are weakly coupled in the UV, okay? So low dimensional field theories is what I'm going to be talking about. And then this matching can be done in perturbation theory, so we can really get our hands on it, okay, and understand what's going on, okay? Okay, I guess I didn't realize that slide was over. Okay, so that's the basic idea. That's the playbook, okay? Now, there's the obvious comparison here is with the lattice, okay? The lattice is currently, so this, by the way, I should have said, the idea is going to be that I'm going to end up with some huge matrix, maybe, you know, in the end, we're going to have like 30,000 by 30,000 matrices, okay? So they're very, very large matrices, and so you just diagonalize them numerically by brute force. So the natural comparison of this method is with the lattice, okay? So let's compare those. So in the lattice, right, we have an IR cutoff because we need to put the system in finite volume so that we have a finite number of, you know, finite system, okay? And then we have a UV cutoff, which is the lattice spacing, right? Now in HT, in Hamiltonian truncation, we use exactly the same IR cutoff. We put the theory in a box of size L, okay? But the UV cutoff is this, the UV cutoff is given by the total energy as measured by the free Hamiltonian. And crucially here, one of the major differences that's going to be really important here is that this ET, which defines the UV cutoff for Hamiltonian truncation, is the total energy, right? The total energy in this box, and that is non-local. So if something is happening over here in this corner of the box, right, and something is happening over here in this corner of the box, then the total energy cares about both of them, okay? And so that is the essential non-locality that is in this method, okay? And we will see that that has consequences, non-locality, but it's not as bad as you might think, but it's not as good as I had originally hoped, okay? And we'll talk about that at the end, okay? Okay, so let me tell you some other reasons, some other things that are, you know, the sort of in the spirit of warts and all, as Michael said at the beginning. So Hamiltonian truncation is exponentially expensive, okay? And for the very simple reason that the number of states grows exponentially with the total energy, right? This is what makes statistical mechanics work, okay? Is the fact that there are many, 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 many excited states, right? Exponentially many. On the other hand, we expect the error, if we truncate at some maximum energy ET, we expect the error to go like some 1 over some power of ET, right? That's the best we can hope for. And putting these things together, we see that you only sort of improve logarithmically in accuracy if you just keep increasing the high energy cutoff, right? Because presumably the calculational cost is growing with the number of states, so it's growing exponentially fast. And so, anyway, you only win logarithmically, right? Okay, so that's bad. So why should you study this with all of these crazy things, non-local cutoffs, exponentially hard calculation? Why should you do this? Why should you consider this method? First of all, we'll see, and other people had already, of course, shown that this actually still gives interesting accuracy in examples. So before you hit this exponential wall, you actually get you can actually get interesting accuracy. So maybe that's okay. You can also think that Hamiltonian truncation, it may be able to preserve symmetries that are badly broken on the lattice, like chiral symmetry for fermions or supersymmetry. And indeed, there have been some investigations along these lines already. I probably should have put some references here, but anyway. And you know, there's the sort of long-term hope that anytime you see one of these exponentially hard problems, you can hope that quantum computing might someday be able to overcome this exponential barrier, okay? All right, so I'm going to continue. I won't be offended if this is already so bad you don't want to hear the rest, but I'm going to continue. All right. Okay. Oops. Sorry, I wanted to say one more thing here. What did I want to say? Yeah, I just want to push this thing as far as it'll go, right? Okay, there was a delay on my end here. Okay, so let's do this in an example theory. It's good. It's really helpful, I think, to develop this in the context of a specific example. So we're going to do 2D 5-4 theory. It's the theory we all know and love, right? And we're going to have in this, since you're not probably living your life in 2 dimensions, I'm going to remind you that the scalar field is actually dimensionless in this case, and the coupling of 5-4 coupling has mass dimension 2. Okay, so this is a super renormalizable theory, or better said, it is very weakly coupled in the UV, right? Because it has a coupling with positive mass dimension. And renormalization is extremely simple in this model. Only tadpole subdiagrams are divergent. Okay, so diagrams like this, and so it means that I can subtract these away simply by normal ordering. So here's my unperturbed Hamiltonian. It's just a sum of harmonic oscillators, right, with frequencies. And then the interaction is just some normal ordered phi to the fourth, right? And that's it. Okay. So this is my Hamiltonian. Okay. And you can see now that my eigenstates are just oscillator states, and I can write phi in terms of oscillators, and so it's very straightforward to construct the matrix of V in this basis and construct the Hamiltonian and numerically diagonalize it. Okay. Okay, so just to let's think about the matching. Okay, so we want to now look at the effective Hamiltonian. So we have our full Hamiltonian that acts on the full Hilbert space. Okay, and notice that this perturbation V is of order lambda, right, which is a weak coupling in the UV. And so my matching calculation is going to be a matching in powers of lambda, or powers of V. Okay, my effective Hamiltonian will be H0 plus H1 plus H2 and so on. This is a finite dimensional Hamiltonian that acts on HT, right? And this H sub n is the order lambda to the n contribution to this, right? Okay. Now the question we have to ask is, what quantity are we supposed to match to define the effective Hamiltonian? And the very first thing that you think of, and the only thing that anybody else has ever thought of or discussed that I know of in the literature, is the energy spectrum. Okay, because one way to think about this, you might say, well, once I have the effective Hamiltonian, it's just a finite, sorry, I clicked there, but anyway, the effective Hamiltonian is a finite dimensional matrix. What else could you ask for except the energy spectrum? But however, I want to show you that matching the energy spectrum is not enough to define the effective Hamiltonian. So to show you that, here's some notation. The full energy eigenstates and the eigenvalues are denoted by script E, and the the eigenstates of H naught are denoted like this with I and E sub I, okay? And now let's just compute this E sub I in the effective theory, in perturbation theory, in this expansion in powers of lambda. So this is something you all do in introductory quantum mechanics. And the first few terms are written here, right? This is just eigenvalue perturbation theory. And what I want you to notice is that, remember, what we want to do in matching is we want to determine the matrix H1, for example, by knowing what these quantities are by matching to the full theory. But we see here that we only get the diagonal element of H1, right? And then at next order, we start being sensitive to off-diagonal elements of H1, but we're only sensitive to the diagonal elements of H2. And so, because of these things, if we match the spectrum order by order, we're only going to be determining the diagonal elements of H sub n. Okay, so somehow the spectrum is not enough information to find the effective Hamiltonian. Okay, so that's one crucial piece of this. There's going to be several sort of crucial steps to constructing this effective Hamiltonian, and this is the first sort of non-trivial crucial step.
I have a question, Markus. Is it okay?
Yeah. Yeah.
So for the so there's H naught for the full Hamiltonian and there's H naught for effective Hamiltonian, but are I'm assuming they are different H naught, right?
Yeah, well, this H naught, sorry, this H naught is just the truncation of this H naught to the finite dimensional space. Okay. So a mathematician would be upset with me, but physicists should be okay with that, I think.
Okay,
right?
so it is truncated.
They are the same in that sense, right? Because these states I are just a subset of the full states, right?
Yeah. Thank you.
Okay. Okay. Okay, so the spectrum doesn't work. Actually, the crucial step is not that the spectrum doesn't work. The crucial step is what does work. Okay, but I guess you have to recognize the problem before you can solve it. Okay, so what is the missing ingredient? And I think it's physically clear if you think about it for a bit. The missing ingredient should be time dependence somehow. Okay, because well, let me just say some intuitive things about that. Because well, maybe not saying intuitive. I think if you think about it for a bit, somehow the energy spectrum is only telling you about stationary states, but there's more to life than stationary states. So somehow time dependence should be important, right? Okay. So I'm going to just tell you what the what I claim is the right quantity to match. Okay, and this was found by trial and error, and so I don't have a beautiful story. I haven't made up a beautiful story of why this is the right thing, but I can show you that it works. Okay, so the idea, well, it's sort of motivated by the fact that I would like something like the S matrix, but the S matrix is not well defined because I'm in finite volume, right? So I need some analog of the S matrix that is well defined in finite volume. So what I'm going to do is I'm going to sort of follow one of the ways of thinking about the S matrix. I'm going to turn off the interactions at late times. Okay, so that's what I'm going to do. Sort of, that's one of the ways that you can define the S matrix. And then I'm going to define this quantity, which I call sigma, which is I take the interaction picture time evolution operator from 0 to t final and take t final to infinity. Okay. Now, if in the S matrix, I would also try to take t initial to minus infinity because I want to scatter from minus infinity to plus infinity. But in this theory, because I'm in finite volume, right, particles can't separate and become free on their own. They don't, right? So at t equals minus infinity, the theory is not going to be in any sense free. So this is like sort of like the square root of the S matrix. It's the part of the S matrix that goes from t equals 0 to t equals plus infinity. And I've turned off the interaction sort of by hand, okay? That is the quantity that I claim we're going to match, okay? All right. And hopefully it's not totally nuts, but the important point is that it works. So you can interpret this as the amplitude to go from an interacting state at t equals 0 to a free state. So you sort of turn off the interactions and let the state fall apart into its free constituents, okay? And this is well defined the claim is this is well defined for normalizable states in finite volume. And one thing way you can see this is just you can construct a perturbative expansion for this, okay, in powers of v in this thing that I'm doing. And so I define this quantity t, which is kind of like this is like s, and this t is like t when I write s equals 1 plus it. This is just some definition of t, and then t has this very simple perturbative expansion like this. Okay, so it just at each term you just add more intermediate states and add more energy denominators like this. Okay, and that formula also shows you that this is well defined in finite volume. Okay. Okay, so that's sort of the first major ingredient here. So any questions on this? Even if you're not my friend, you can ask me questions. I appreciate all these questions I'm getting from people I know. Okay.
Hello, Markus.
Hi.
Just have a question. When you put t initial to 0, it seems to me that you can describe systems that already interact, not a scattering in the common sense that used to be initially free.
Yeah, I mean, for me, I'm not really focused on this sigma thing as some physical quantity that is going to give me something interesting. I'm just focusing on it as the thing that I'm going to match, you know, and then once I match, what I'm actually going to be interested in are just the low-lying eigenstates of the full Hamiltonian. So I haven't really thought much about using the sigma to somehow the sigma itself to measure something interesting. But in some sense, yeah, it's kind of like it's telling you the content. If you have some interacting state at t equals 0, it's sort of telling you its content in some sense. Is that what you're asking? I'm not sure.
Yeah,
This
thank you.
is John Killich, right? I can't see your screen. But
It's
sound like
Fayez.
John. Hi. It's Fayez. Hi, Fayez. Sorry. I'm
nice
sorry. You sound a little bit like John Killich.
Right.
Yeah.
Thank you.
Okay. All right. Okay. All right. Okay. And then I just want to say that now, if you match this quantity, you determine the effective Hamiltonian completely. So just like you do this eigenvalue perturbation theory, you can do matching for this this quantity sigma or t that I just defined. And you see that the lowest order, the formulas look similar, but there's now, notice there's an IF here. So H1 is just V value, is just the raw truncation of V, which is what you would expect, okay? And at higher orders, again, the full effective theory is the full effective Hamiltonian is determined, all the matrix element, right? Now notice that this H effective, these H1, H2s, and H3s are not Hermitian, okay? Because if you look at these energy denominators, you notice that they always prefer F over I, right? There's this, so these are not symmetric in F and I. These are not Hermitian, okay? So that may be a bit disturbing, okay? But actually, if you think about it, it actually makes sense because time evolution does not keep you inside this truncated Hilbert space, because the truncated Hilbert space is made of eigenvalues of H naught, but time evolution proceeds with H. So there will be some leakage, in and out of this effective space. So I think that it is a feature, not a bug, that this Hamiltonian is non-Hermitian. At leading order, it's Hermitian, right? But then at higher orders, it's non-Hermitian. Okay. And actually, in terms of when we were stuck for a long time, and for me, we actually realized first that the effective Hamiltonian could not be Hermitian, and that sort of freed us up to thinking about this weird matching quantity. The origin of this non-hermiticity is sort of built into the quantity that we're matching, okay? Because remember, the quantity we're matching starts at t equals 0 and turns off the interactions at late times. So there's a definite asymmetry between the initial and final state built into sigma, and that reflects itself in the effective Hamiltonian. Okay. All right. So, okay, so now let's talk about how we actually do the matching. So in principle, I've showed you formulas for the matching, okay? But I don't have to convince you, I hope, that diagrams are useful, right? So we want to have a diagrammatic expansion for this matching quantity and understand the matching diagrammatically, okay? And it's not going to surprise anyone who's ever spent any time looking at old-fashioned perturbation theory or time-ordered perturbation theory, right, that this expansion is going to be very, very similar to old-fashioned perturbation theory, okay? And so we're going to have interaction vertices that are ordered in time. Energy is not going to be conserved at the vertices, right? But spatial momentum is conserved, all right? And so, for example, if we want to look at the diagrams, the order lambda squared diagrams in 5-4 theory, we have all these separate diagrams here, right? Because, because we're time ordered, we have to permute all the initial and final states. Those are different diagrams, and so on. Okay, so I'm going to sort of give you a feel for what the Feynman rules are. They're explained very, very probably too explicitly in our paper, but anyway, they're very explicitly explained in our paper. But just for this talk, let me give you an idea what the rules are like by just doing an example diagram. So let's do this diagram, okay? So I want to go through this a bit slowly because doing this diagram will also sort of illustrate some of the features of this matching that are going to be important that we'll see later. So here's a diagram. We have two particles, excuse me. We have two particles coming in and interacting. This is okay. But now we have to remember that this is being sandwiched between initial and final states that could contain any number of particles, right? So we could have an initial state with 1 million particles, or maybe not 1 million, but maybe 10, okay? And so in this diagram, there are these other particle lines. This is the initial state, this is the final state, right? Quantum mechanics always goes from right to left. And these states here don't interact, right? They just kind of go through, but because my interaction only involves 4-point interactions, only a handful of particles actually interact, okay? And so now I have an initial state here, an intermediate state here, and a final state here, okay? And now here's the diagram, okay? So this is a lot, but let me just say here's some symmetry factor, there's some coupling constant factor. Now I assign a spatial momentum to each line, and I sum over all the spatial momentum. I have a delta function for the spatial momentum at each vertex. Okay, I have a sort of external state factor, which consists of the matrix elements of these positive and negative frequency states. And what those are just creation and annihilation operators. Okay, so this matrix element here is a matrix element in terms of creation and annihilation operators. That's a matrix element that I need to evaluate. And then I just have a propagator factor of 1/2 omega for each internal line. So I have those, okay? And then I have an energy denominator that has to do with the difference between the final energy and alpha. Okay, the energy denominators are, if I have more than one intermediate state, there would be an additional energy denominator between F and beta, okay, and so on, okay? And the reason I don't have one between alpha and I is because in the definition of T, I factored that out, okay, that's it, okay? So that is the Feynman rule for this diagram, okay? Now, one of the things that you notice is that this factor here depends on EF. EF alpha is EF minus E alpha. Okay, so I hope that was obvious, I hope. But anyway, it depends on the total final energy, right? But actually it doesn't, because EF alpha is the difference between EF and E alpha. And then all these additional particles that are going through, they cancel out. Okay, so in this diagram, there is no actual dependence on the, so sorry, oops, I didn't mean to do that because I'm giving away my, okay. So in this diagram, there is actually no dependence on these spectator particles at all. Okay, all right. However, this is actually the diagram in the fundamental theory, right, where I have the full Hilbert space. I have exactly the same diagram in the effective theory to do as well, right? And in the effective theory, the only difference is that I have to put in a step function that restricts the intermediate states alpha here to have energy less than E total, okay? All right, now E total minus E alpha can be written in terms of EF alpha, okay, as above, but it really does depend on EF. There's no way around it, right? And intuitively, that's obvious. If I want the total energy alpha here to be less than ET, then it counts the energy of these spectators, right? Okay. And so that is the origin of the non-locality. Remember I said this thing is non-local because the cutoff cares about particles, distant particles. So I can look at this diagram as saying, well, here's this interaction that's taking place on Earth, and these particles are, I don't know, on Mars or something, okay? But to know whether I need to keep these two particles in my effective theory here on Earth, I need to know what the energy of these particles on Mars is, okay? That is non-locality. But the claim is this is the only source of non-locality, okay, in this diagram. In the full theory, I don't have any non-locality, which makes sense because I'm just calculating the full theory in some goofy way. But in the effective theory, I do have non-locality that's related to the cutoff, right, which makes sense. Okay, this is the second sort of important major step in this sort of story that I'm telling. Okay. Okay, all right. Any questions on this? Okay, all right. So now
Markus?
let's go. Yes, sorry, please.
Markus, hi. So isn't this more than non-locality? Isn't this a violation of cluster composition somehow? Your example between Earth and Mars.
Yeah, very good. I mean, but cluster decomposition is a property of the S matrix. So I think, yes, I think you could say it that way, but you know, it's again a fact that it's related to the fact that I'm in infinite volume, right?
Yes.
And so I don't really have, you know, cluster decomposition is saying what happens when things go to infinity. Here they can't go to infinity, spatial infinity, right?
Yes. Okay, thank you.
Okay. Other questions? I think we're going to have lots of time for questions, so please do interrupt me I guess, is it embarrassing to finish early? Does that mean like you don't have very much to say, or is it just making
Nope,
everybody
it's perfect. It's whatever you
I
wish.
can ask a question.
Yes.
Now, if you have a non-local theory, you're gonna violate causality unless you have some high scale of suppression that makes emergent theory at least macroscopically causal.
Well,
How do I
so-
see this?
Yeah, yeah, I used to, I'll make this joke now. I forgot to make it earlier. You know, usually if I go to a talk and somebody says they're talking about something non-local, I just feel like I want to leave, right? Because as soon as you start talking about non-locality, the feeling is you don't know what you're doing anymore. Every possible terrible thing happens, okay? But actually what we're going to find is that here, first of all, I want to say, why is this okay? Why is this better than that kind of a talk? Because I am matching to a local theory. So my theory is this non-locality is there to reproduce features of the theory that's local. So I want to claim that these are there because I'm taking something which cannot possibly be local. It's a finite dimensional matrix, okay? That's the Hamiltonian. It has no notion of locality, and yet it is trying to match something that is local. And all these weird features here are a consequence of matching to something that does make sense, okay? And the second thing is I'm going to claim, and we'll see later, that all of this non-locality is under control in an effective field theory expansion, okay? All right, so you know, there's that, yeah. Okay.
Yeah, so I can think of it as an artifact of the expansion, more of the underlying theory.
Yeah, I think that's the way to think about it. It's an artifact of the fact that I'm trying to approximate a quantum field theory by a finite dimensional matrix.
Thank you.
Okay. All right. Okay. So now let's just talk about some bread and butter matching. So how do we match? Well, we evaluate the same quantity, which now is this weird scattering matrix T. We evaluate it in the fundamental and the effective theory, and we set them equal to each other, right? And so an important point is that we match at low energies, right? Again, I'm hoping this is all bread and butter for everyone. So the external momenta of all the external particles are small compared to the cutoff when we evaluate these diagrams. Then we see that for example, we have this diagram in both the effective theory and the fundamental theory, but in the effective theory, we have some additional counter terms, right? And those are the terms those are the effective Hamiltonian matrix elements that we're trying to compute. And so in this example, the effective Hamiltonian matrix element is a difference, right, between diagrams in the fundamental and the effective theory, okay? And this is an important conceptual point because these two diagrams, we know they behave very, very differently in the UV for states that are near the cutoff, but they have the same dependence on the IR intermediate states here and here. And so the dependence on the low energy states is going to cancel in this matching, right? So that is a crucial feature of matching. It's the separation of scales. It's telling us that the coefficients in the effective Hamiltonian only depend on the physics of the states near the cutoff. They don't depend on IR stuff, okay? All right, and so I want to show you that this does in fact work in this effective theory, okay? So for example, let's do literally those diagrams that I just talked about, okay? And then there's a lot of stuff here, okay? But what you should focus on is that there's this step function, and the step function basically says that only the high energy states contribute, okay? So to make that a little bit more clear, let me say that energies 1 through 4, and also the total initial and final energies are all assumed to be small compared to the cutoff, right? And so then the things that are required to be large is both K5 and K6, the momenta in these lines have to be large. And so these quantities here in blue all have to be large. And we see that basically this theta function is saying that omega 5 and omega 6 are both large. I think I said that here. Okay, well, I didn't say, okay. So these omega-5 and omega-6 are large, and then all these things that are not in blue, I can just expand in powers of them. So this is the usual thing we do in effective field theory. We just expand in the IR scales, okay? And the leading approximation for that is just we set all the IR scales to 0. That's the local approximation. When we do that, we get a local result, okay? So we have to add together all the different diagrams with all the different initial and final states, and we find a very simple result, okay? We find that we get a counter term, which is just normal ordered phi to the 4th with some coefficient, okay? And the coefficient involves only the sum over UV states. Any questions on this? Okay, all right, and okay, and there's even an analytic expression for that. It's very simple, okay? Now, there's also some things that are not so simple.
Sorry,
Okay.
Markus, another
Yes.
question. So can you
Hi.
go back one slide?
Yeah,
Yeah, so can, at this order that you're displaying at the bottom, so can this be, so this is essentially a renormalization of lambda?
yes.
Okay.
I'm going to build up to normally in effective field. I'm going to show you the sort of full power counting and so on at the end. Okay, so
Okay.
right now this is just the answer. If you do this diagram plus all the other order lambda squared 4-point diagrams, this is just what you get. Later on, I'll talk about the sort of general power counting rule. Okay.
And sorry, just to understand and compare to, let's say, standard renormalization of lambda phi to the 4th without Hamiltonian truncation, there is no log. Ah, no, but because here we are in 1 + 1, so there is
Yeah,
no
here
running
there
of
shouldn't
lambda
be.
anymore.
This is
Yeah.
morally no different from at all from ordinary matching.
Yes.
Okay, there's some
Okay.
the detailed differences, but yes, you're exactly right. You would get an exactly an answer of this form if you did
Okay.
ordinary.
Thank you.
matching.
Thank you very
Okay.
much.
Okay, but now we're going to start seeing some differences. Okay, when we go to more complicated diagrams. Okay, any other questions on this before I go to more complicated things? Okay, so now let's go to 2 loops, okay? And this is the highest loop order. Actually, we went to 3 loops, but anyway, let me just talk about 2 loops, okay? Now there's a new issue, okay, for people who are real, who really know about perturbative matching. You know about this, because now we have in a 2-loop diagram, okay, even though we're subtracting these things, there are now mixed or overlapping UV-IR regions, right? Where, let's say, for example, this energy and this energy is large, but this energy is small, okay? And that region does not cancel between this diagram and that diagram, right? The same issue occurs in renormalization theory. This is the issue of overlapping UV divergences, okay? All right. And so what I've, to make the expression relatively simple here, I've immediately gone to the local approximation. So I've set all the external momenta to 0, okay? And then what you see is that this theta function only constrains the sum of these omegas to be large, right? But that could be 2 of them are large and 1 of them is small, okay? So the UV-IR mixed regions do not cancel in the matching, okay? All right, but this same effect for this exact same diagram also occurs in conventional EFT matching, right? And we do believe in the separation of scales in ordinary EFT. So we are not worried, we're not scared. We just keep following the EFT playbook, right? We just keep going, okay? Now there are some new ingredients here, okay? First thing is that we should revisit the renormalization of this theory. It was trivial, we did it by normal ordering, okay? But when we follow the EFT playbook, one of the things that we learn is that we should have a floating renormalization scale, mu, and we should renormalize, right, when we match, okay? Sorry, we should match, don't I say this? Sorry, I don't know what's going on. Hold on, my thing seems to be stuck. There we go. Okay. So to get the separation of scales to work in EFT, we need to take the floating matching scale to be of order the cutoff, right? When we do the matching. Okay. However, the normal ordered mass is basically the renormalized mass at mu equals 0. Okay, so we're going to get some artificial, we're not going to sum the large logs, if you like, would be the normal way we say it, unless you choose the renormalization scale to be ET. Okay, so we should actually write things in terms of this MR, not in terms of this normal ordered mass that I've been using up till now. Okay, and so what that means is we have this new counter term that depends on this, that depends on various things, and we have a different mass, which we call the quantization mass, that is the thing that appears in the diagrams. That's now like the renormalized mass in the diagrams. This is a bit of a detail. I don't think I should have put this in here. But anyway, the important point is that the claim is that the separation of scales, namely the idea that these coefficients in the effective Lagrangian are just some are sensitive only to the physics at the cutoff. This only holds for operators renormalized at mu equals ET, and also it only holds for non-normal ordered operators. The normal, one way to say that is normal ordering is some goofy way of renormalizing at mu equals 0, and that's not what we want. Another way to say it is normal ordering is only defined in terms of this non-local object H0. It's just not, you know, separation of scales is locality. And anyway, we claim that the separation of scales only holds for the non-normal ordered operators. That's the claim, okay? And so, for example, so we expect the effective Hamiltonian to look like phi squared phi fourth. Notice no normal ordering, okay? We already showed you what lambda 2 is before, okay? Here is what M2 is, okay? I'm not expecting you to read all of this and parse it, but I'm trying to tell you that this first term comes from that diagram, the one that I showed you, and it indeed has these overlapping UV and IR regions, okay? But now there's this diagram, which has this additional counter term that I need because I'm normal ordering. This also has a UV IR overlapping region. And then finally, there's this term, which comes from converting the normal ordered phi fourth to ordinary phi fourth. That corrects this term and gives me an additional contribution, which also has an overlapping UV-IR regions, and all three of these together cancel, okay? The mixed UV-IR regions cancel when I add all three of these things together, okay? All right, and the claim is that this is what corresponds exactly to what happens in ordinary QFT, ordinary matching, I mean, okay? And that tells me that the counter term really is dominated by sums where these omegas are of order ET, okay? So we don't have a nice formula to show you for this because this is too complicated, but we can just numerically evaluate it. That's what we'll do at the end of the day, okay? And we also checked that this is true even for this 3-loop diagram. So this 3-loop diagram, there are multiple regions where you can have overlapping UV-IR divergences. When you follow this procedure, you find that they all cancel, as I claim they should, okay? Okay, good. All right, so now finally, I'm going to tell you about power counting, okay? And let me emphasize that this is just for the 2D phi 4 theory that I'm talking about. So I'm going to generalize this a bit later in the talk, okay? But we have this Hamiltonian, which is a sum of effective Hamiltonian, which is a sum of terms with various powers of lambda. What do they look like, okay? So here's the idea. I'm going to unpack this slowly, okay? Of course, h to the n is proportional to lambda to the n. And I've put in a power of the cutoff so that this has the correct units, okay? All right. And then it is an integral over dx, okay? Now, for a moment, let's forget about this argument. This is just a coefficient, okay, times some operators, okay? And the operators are functions of the field phi, which is dimensionless in this case, and some and derivatives. What else would it be, right? So this is all perfectly conventional, okay? Now, what we expect in an EFT, right, is that the coefficients of these operators can also be expanded in powers of the IR scales divided by ET, right? So ET is the UV scale, and we have IR scales, for example, the mass M is a UV scale, so the coefficient can depend on M over ET. R inverse, R is the radius of the space, right? L is 2 pi R. That is kind of like the KK mass, the lowest lying KK mass. That's also an IR scale, so we can expand in R inverse over ET, okay? So far, everything is just like in a local cutoff. Now here comes the new feature. The coefficient is not really a coefficient. It depends on H naught. So the coefficient here is really an operator, okay? Because remember those powers of EF that I got in the Feynman rules? Well, EF is just H naught acting on the final state, okay? So those powers of EF turn into powers of H naught in the effective Hamiltonian. So that is your non-locality. There's your non-locality right there, okay? It's very, very non-local. It's also Hermitian, by the way, because H naught is to the left of O, and I really mean that. I mean, this is not some, there's an equal sign here, okay, right? I really mean it. And so this is non-local and non-Hermitian, but it's controlled in expansion in powers of 1 over ET. That's the crucial point, okay? That's why this is not a crazy non-local talk, hopefully, okay? And so let's just write out the first few terms. So this is the point I've been trying to make, is that everything is just, all these weird features are just there to match the fundamental theory, and they're under control in a systematic expansion in powers of 1 over ET, okay? All right, so let's, there's the non-locality, okay. All right, so and these powers of H naught come from these powers of EF. That's what I said. I should have clicked through this as I was saying that. Okay, so for the phi-4 theory, H2 has all the terms that are of order lambda squared, okay? And by dimensional analysis, we could have phi to the 1 million here, but we don't get it because we have only a phi-4 interaction, right? If we had a phi to the 1 million, that would actually be just as super renormalizable as phi to the 4th, but we don't, okay? So we only go up, so that's an artifact of the fact of the special theory we're choosing, that we only go up to phi-4, okay? Then we start having some terms that are inverse powers of ET, okay? R naught with R inverse and H naught, okay? And I guess I should have put M here as well. I don't know why. There's also M, just like I have here. I don't know why I omitted that. And again, we only go up to phi-4. Okay, these are suppressed by an additional power of ET with this. So the terms that I'm omitting are even higher. They're 1 over ET to the 4th. Okay, and if you look at H3, you can just check that all of them actually start at ET to the 4th. Okay, so it's actually kind of interesting that we're going to be looking at just these terms right here. Those are the things that we calculated with the diagrams that I've already showed you. But to go to higher orders, you actually just have to expand those same diagrams to higher orders in the IR scales, okay, which we haven't done yet, but we're doing it now. Okay. Okay, so
Markus, I don't want to interrupt, but you're just about 5 minutes out from 5 o'clock. Just to
perfect.
I'm
5 minutes. I'm less than 5 minutes away from the end of the talk. But thanks for the reminder.
awesome. Okay, great.
Okay. So so we're just going to now see how this approximation works with numerical computations. Okay. All right. So that's going to be quickly just the rest of the talk. You might say, okay, great. You've matched this weird quantity, which is some weird asymmetric time evolution operator. You've got some matrix, but maybe this matrix has nothing to do with the fundamental theory. Okay, so let's just check it with some numerical computations. Okay, so notice that the raw truncation is just H naught plus H1. How big should the error be there according to this power counting? Well, the next correction is H2, which starts at 1 over ET squared. So it should happen that if I do the raw truncation, I just keep H naught plus H1, I should get an error of order ET squared. But then if I include these terms, then the leading correction come from these terms, and the error should be 1 over ET cubed. So I should see a dramatic increase in the accuracy when I add this term H2, which we calculated in terms of all these weirdo diagrams that I just showed you, right? Drum roll. Okay, of course I wouldn't be doing this if it didn't work. Okay, so here are some here's some plots that show you that it works. So this first diagram here that shows you here I'm increasing, here Emax is ET, it's the same thing. As I increase ET in some units, I see that this goes, the raw truncation does improve, but here's the improved one is better, it's improved. Okay, now from this plot, you can't see what the powers are. So to see the powers, I plotted the error in the raw truncation as a function of 1 over Emax squared, and the error in the improved approximation as a function of 1 over Emax cubed. And you see that they are very nicely straight lines, okay? This was for one particular choice of parameters, okay? It works for other choices of, this is for excited states for the same choice of parameters. That was, the previous plot was the ground state. Here are excited states. They also do the same thing. This is a plot that shows you the full spectrum as a function of lambda. So we looked at different powers of lambda. The same thing works for different powers of lambda. And you can see that in my units, the critical point is happening around lambda over 4 pi is 5. Okay, so that is sort of where you might expect it by sort of NDA type arguments. And you can see that the accuracy does sort of degrade when you increase lambda, but you still see this linear behavior, linear convergence in the improved thing with the correct power. Okay, so the slope is not a parameter here. The slope is given by the expectation that the error is 1 over E cubed. And if you look at the vertical axis here, let's look at this plot here, you see that we have a lot of accuracy. So we didn't do try to do an extrapolation and quote an error, but you see we've got error here easily in the 3rd or 4th decimal place. Okay. Okay. And these extrapolations agree, et cetera, et cetera. Everything works like a dream. Okay. Okay, so now I'm going to conclude the next steps. Okay, so one thing we're definitely, two things that we're currently doing. One is to just go to next order in this 2D theory. I sort of already talked about that. Okay, we have to include these terms. Okay, and notice that you might say, well, who cares? Well, the reason I care is because, see, the terms we already computed are local and Hermitian. Okay, even though I advertised all this non-locality and non-hermiticity, these terms happen to be local. So you might say, well, it's going to fail as soon as you have non-locality and non-hermiticity coming in, but that's what's happening here. Okay, so these terms are both non-local and non-Hermitian. Okay, the other question was one that was asked earlier in the talk by Takamichi Ukui. What about renormalization? So if we go to 3D 5-4, okay, then if we do the power counting, then at leading order, we get things that diverge with ET. We have now true UV divergences, okay, right? And in this theory, the leading, we cannot do a raw truncation. A raw truncation would give nonsense, okay, because the error grows with ET, right? But if we include these divergent terms, we should get an error of order 1 over ET. Okay, so that again involves going to higher order, and that's a calculation that's in process. Okay, they're UV divergent, non-local, and non-Hermitian. Okay, so if this works, it's a proof. It's a mathematical, rigorous proof that this method is correct, right? By the standards of EFT. Okay. Okay, so now in my last 1 minute or -1 minute, I'm going to talk about future prospects, okay? And you know what often happens, we spend a lot of time on this. I think we did something that I'm happy with, it's non-trivial, but then you have some time to think about it, and then you realize that maybe it's not as awesome as you thought it was. So anyway, that's what happened to me here. So let's just cut to the chase here, right? What do we really care about? Could we ever compete with lattice QCD, right? Let's ask that question, okay? Or let's see how far we could get, all right? And so in lattice QCD, what does this effective Hamiltonian look like? Well, the bare coupling is now dimensionless, and I'm in 4 dimensions. So my effective Hamiltonian is a cubic integral, and it has all these divergent terms, right? So this term doesn't scare me because it's just a cosmological constant term, but all of these other terms here, cubic divergence, quadratic divergence, linear divergence, log divergence, all of these have to be, all of these would have to be computed very, very precisely, okay, in order to get an accurate answer, okay? And the coefficients in these can in principle be computed in a weak coupling expansion, but the weak coupling only goes to 0 logarithmically with ET. So this is just my answer to this. Can this ever compute with lattice QCD is no. But on the slide, this is the price. Okay, so I'm going to say that later. But on the slide, I'm going to say probably not. If you talk to lattice people and you tell them you need to fine tune one quantity quadratically, they say forget it. Like Wilson fermions, forget it. Wilson fermions may even just be linear, I forget. But anyway, forget it, okay? So now this, I think, is just the price of a non-local cutoff, okay? Because these are these very non-local terms. They are under control. It's not infinitely bad because there's a finite number of these guys, okay? So there is something very non-trivial that happened here, I think, but I don't think it's enough, okay, right? Maybe someday with some quantum computer in the year 5050 or something, I don't know, okay? But, okay, so that's my unvarnished take on the long-term future of the subject, but I think it's still interesting for super renormalizable theories. I still think we want to think about, for example, gauge theories. There are lots of theories we can still have fun with. But for me personally, I mean, honestly, my takeaway from this is that what this has gotten me to do is to think about, I think we've learned some lessons here that are maybe more generic than this, you know, because ultimately when we do, so for example, lattice gauge theory, we have to do these various numerical truncations. And we just think of them as something that the computer guys need to worry about. But actually, they are some kind of weird effective theory that are also turning an infinite dimensional problem into a finite dimensional problem, right? And what I've shown here is that you can understand that in the language of EFT. And I don't need to tell this audience that it's always useful to write something in the language of EFT. You guys are already convinced, so I don't need to convince you. And that's, to me, the biggest takeaway for me personally from this. And that's it. So thank you very much.